Hello and welcome to Physical Geology. I am Robert Lopez. So here I want to introduce our textbook, Chapter 1, and the study of geology. So remember, geology, we're looking at not just the surface of Earth and the interior of Earth, but also the processes involved in making these landforms and creating sedimentary rocks and the origin of magma. So we have to understand not just the interior machinery of Earth, which really has to do with the release of heat, this internal heat engine that we have that drives plate tectonics, builds up mountain ranges, causes continents to collide, and opens up ocean basins. So all that's in plate tectonics. But also we're concerned with the surface processes, that weathering and erosion of the mountains to produce sediments, and how these sediments are moved around and how they're deposited in unique environments of deposition. And by just looking at the type of sediment, geologists can interpret the environment, whether it was a marine environment, a land or terrestrial environment, or whether it was in the deep parts of the ocean or shoreline, shallow levels, glaciers, arid climates. So we understand all that just by looking at the minerals in the rocks, these materials of geology, of earth science. But it's not just the rocks and minerals, but it's also the water on Earth. Where did the water come from? How's the water moving? What are the different reservoirs of water, resources? Obviously, water is important because as humans, we rely on water for drinking and for growing our crops. And so the first part here really discusses what geology is and how really geology encompasses all these different other sciences. There's physics, chemistry, biology, mathematics, astronomy. All those go into geology. So a geologist has to have a really good understanding of these different sciences and different topics. Now, for geology, remember, we're not just looking at how the rocks are being formed, how the mountains are being pushed up, the origin of the magmas, but we're also seeing this third dimension, which is time, and how even these slow rates of like glacial erosion and sedimentation may happen only in millimeters per year or centimeters per year, given the vastness of geologic time, millions, hundreds of millions, billions of years. It makes a dramatic difference. So we can interpret the processes, and then we have this third dimension that gives us that geologic time, that scale. So you can read a little bit here about geology and the slow processes. And then there's a little bit about the scientific method. There's a quiz on Chapter 1 that is really based on these readings. And I have several questions that are about the scientific method here. The key thing with the scientific method is that I need you to understand the difference between a theory and a hypothesis. So in science, a theory is one that's been tested. It's made predictions. It's held the test of time, right? So it's supported by facts and evidence and observations. Whereas a hypothesis is what most people think of a theory. When people think of a theory, they're really thinking of a hypothesis. And a hypothesis is an explanation, or at least here it says a tentative explanation that could explain the observation, right? So we need to test those. That's the key thing about these hypotheses, that they must be testable here, must be testable. So that's what we're looking for there. So why don't you read that, and you can answer the questions on the quiz. Why do we study Earth? Well, resources. I mentioned water. We need water for our crops, water for drinking, water to live. But we also need minerals. Basically, one of my professors in college would always say, if you don't grow it, you mine it, right? So you have to get it from the earth. The lead in your pencil. When you flip the switch on for the light switch of your light, what you're doing is you're really burning some sort of fossil fuel. Well, that's coming from the earth, right? So really, resources, physical resources, drive our modern economy, right? So we need to understand that in terms of resources and materials that we use. But the other side of geology is really natural hazards, like this picture here of a landslide that happened in 2005 in Vancouver. Unfortunately, the author says here that there was a report done in the 1980s that said this area was susceptible to these landslides, and there was no retrofitting or no work done to support the structures, and sure enough, the landslide happened in 2005. So geologists also study Earth to make predictions or assess hazards like volcanic hazards, earthquakes, landslides. So what do geologists do? So many of them work for oil companies or mineral resource companies looking for those resources. Some geologists work for governments to mitigate natural hazards, the resources for water, groundwater. Some geologists are working for private companies for assessing landslides or developing methods of retrofitting and shoring up slopes to prevent landslides and mass wasting. And others are working as instructors, post-secondary level here. This next part deals with a little bit of background material on minerals and rocks and plate tectonics and different parts of the textbook. The key thing for minerals and rocks, and we'll be doing this week, is that there's really this four-part definition of a mineral. It's, number one, naturally occurring. Number two, it has some specific chemistry, some specific elements. Number three, it's not on here, but it's inorganic. It can't be made by some organism, so it's an inorganic solid. And here, number four, it has this three-dimensional structure called a lattice, and that's what I call the crystalline property. It's a repetitive internal arrangement of atoms, and they're all going to be repetitive in the same fashion. And for example, this is salt. A little grain of salt are cubic, and that's because the lattice or the crystalline structure of halite, which is common table salt, is this cubic lattice or crystalline structure. Minerals are important is because rocks are composed, or they're aggregates of minerals. And to understand rocks, we needed to understand what type of minerals they contain. And the different minerals, again, are forming under different environmental, physical, chemical pressure, barometric conditions, so they can be identified in terms of their origin. Now, here's a picture of an aggregate of minerals, which is a rock. You can see there's some quartz grains, some feldspar, so it kind of names them all here. And so here are the individual minerals: hornblendes, quartz, and feldspar, plagioclase feldspar. And here you can see them in the rock here. And so, again, when we're looking at rocks, we'll talk about the rock cycle and how we originate with magma. Magma cools and solidifies to form igneous rocks like basalt and granite. Then this may be weathered to produce sedimentary rocks like sandstones. And then maybe this rock may be buried deeply and metamorphosed to a metamorphic rock. So we'll talk about all these as we go along there. For the next part here, this fundamentals of plate tectonics, well, again, in chapter 10, we'll cover these in more detail, but we need to have a basic understanding. And one of the first things I want you to think about a slice of earth here, where we have from the crust all the way down to the core. And so that radius is about 6,400 kilometers, 6,370 kilometers here. And you can see that there's going to be three fundamental layers. There's this crust, the mantle, and the core. Three, really I call those chemical layers because they're different in their chemistry. The crustal rocks are much lighter and they have lighter chemical elements. The mantle has a little bit heavier elements, more magnesium and iron, whereas the core has primarily iron and maybe some nickel metal. So those are the chemical layers of Earth: crust, mantle, and core. But you can see that there's also some physical layers that depend on some of the properties of the rocks. There's going to be an inner solid core, so that's solid, an outer liquid core where there's convection and that causes our magnetic field for the Earth. Then there's the lower mantle, which is solid rock here, the upper mantle, and then we also have the lithosphere up here. And you don't show here, but there's one layer down here called the asthenosphere, which you see down here. So lithosphere, asthenosphere, outer core, inner core, lower mantle, all those are examples of physical layers. So you can sort of read about what's going on here for the different layers of Earth. The other thing is we do have this idea of heat flow and this idea of convection. So because the core, in fact, the temperature of the core is about the same temperature as the surface of the sun. Very hot. So heat is escaping, heat is moving, and it comes up. And usually where we see the manifestation of the heat rising are these mid-oceanic ridges, or maybe if it's under a continent, you're going to see a rift, like the East African rift in East Africa, where the continent is being torn apart there. Where you see the heat or the asthenosphere cool and start to descend back into the mantle, that's what we have maybe these ocean trenches, these convergent margins called subduction zones. Right here's the subduction zone, ocean trenches. But this whole process is called mantle convection. And that may be one reason what's causing plate tectonics. You'll see there's some other ones that I talk about later on. The Earth is going to have this geothermal gradient. It's about 30 degrees centigrade for every kilometer in the crust. It's a little bit less than that once you get into the mantle. But we'll talk about that later on. For geologic time, remember, it's hard to think in terms of millions, hundreds of millions, billions of years. I mean, we think of the Egyptians, about 7,000 years ago as ancient, but really that's nothing in geologic time. There's James Hutton, one of the fathers of geology here. He has a quote saying that there's no vestige of a beginning and no prospect of an end. He's known for that quote there. But he really kind of developed this process called uniformitarianism. And this process of uniformitarianism is he observed physical processes like weathering and erosion of exposed rocks, and then they're deposited in a stream bank and end up in the ocean. And he thought, after how long would it take to make a thick sandstone layer after, so he imagined this would take millions of years. So that's where you get this idea that Earth must be very old. So you can read a little bit about the different geologic times here, and I'll ask you about the scientific notation that we use here. In fact, there's two terms I want to talk about here. Is this MA. Geologists use this term MA to refer to millions of years ago. A mega annum, so which is 1 times 10 to the 6 in the scientific notation, which is a million. And then GA to refer to giga annum. So giga is 1 times 10 to the 9. So that's a billion. So this would be 4.57 billion years. And that's about the age of Earth, or 4570 MA, or 4.57 GA. So we'll come back to those so you can understand. And then also there's kilometers, or KA for kilo annum here, for thousands of years ago.